Right now, our galaxy drifts inside an invisible continent of galaxies so vast it bends the flow of cosmic matter. Its name is Laniakea, Hawaiian for immeasurable heavens, the largest gravitational domain we have ever mapped. Picture a cosmic rainforest where tens of thousands of galaxies are strands in a sprawling root system, all flowing toward a single gravitational center like rivers seeking the sea. Laniakea stretches far beyond imagination. A supercluster so enormous that light itself requires hundreds of millions of years just to cross it. It forces us to rethink what a place means in the universe, how galaxies move, and what defines an actual cosmic boundary. Tonight, we will explore the filaments that weave it, the mysterious great attractor pulling everything toward it, and why knowing its true size changes our understanding of the universe. If you enjoy these cosmic journeys, hit like and subscribe. Let's begin. Imagine zooming out from every star, every nebula, until galaxies themselves become grains of cosmic dust. In that perspective, the universe stops looking random. Patterns emerge. Streams of galaxies bend and arc, moving not aimlessly, but along invisible gravitational rivers flowing through the darkness. You've been taught to imagine the universe as chaos, galaxies flung outward by the Big Bang, drifting like embers from a dying fire. That picture is wrong. When you zoom out far enough, the chaos dissolves. A deeper order appears. Galaxies don't wander, they fall. Not down, not sideways, but along colossal currents carved into space-time by gravity itself. Think of a raindrop on a mountain. It doesn't choose its path, it follows the terrain. First a trickle, then a stream, then a river, downward, always downward. Galaxies behave the same way, except their mountains are made of matter, and their rivers span hundreds of millions of light years. Scientists discovered this when they calculated where galaxies were going, not where they are. They measured deviations from cosmic expansion, velocities that break the rulebook of a uniform universe. Every galaxy is moving outward with the stretching of space, yes, but some move more than expansion alone should allow. Some veer, some accelerate, some plunge toward distant gravitational basins like comets caught by unseen suns. These deviations have a name, peculiar velocities, and they are the fingerprints of something massive, something ancient, something pulling. You cannot see these currents with your eyes. They are too enormous, too slow. A galaxy can spend 2 billion years in transit and barely cross a fraction of its path. From Earth, everything looks still, frozen, silent. But on the cosmic timescale, galaxies glide like icebergs beneath the waves, obeying a force they cannot escape. Astronomers mapped these flows the way oceanographers track tides. They took thousands of galaxies and drew arrows, direction, velocity, destination. The arrows converged, not randomly, not gradually, but like iron filings snapping into alignment around a magnet. The universe was not drifting apart. It was falling inward. This revelation shattered everything. Galaxy clusters, those bright knots of hundreds or thousands of galaxies, weren't isolated cities. They were waypoints. Rest stops on a pilgrimage governed by gravity on scales humanity had never measured before. Because every current has a destination, every stream has a basin, every flow has a terminus. Follow the rivers long enough, and you reach a structure so vast that the word cluster becomes meaningless. A shape so massive, it requires a new vocabulary. A continent of galaxies stitched together by motion, not light. If you could stand outside the universe and look down, you would see them. Threads of matter twisting into a cosmic delta. Thousands of galaxies bending toward the same invisible shore. That shore has a name, and it rewrites everything we thought we knew about where we live. When astronomers first traced these flows, they realized they needed a name that captured something sacred, something beyond measurement. They chose Laniakea, immeasurable heavens, a word as soft and enormous as the structure itself. Laniakea is not a metaphor, it is a map of destiny, a gravitational basin that contains over 100,000 galaxies, all of them caught in the same slow descent toward a hidden core. Andromeda, the Virgo cluster. Whole chains of filaments stretching for hundreds of millions of light years. Every object falls the same way, drawn not by proximity, but by fate. This was not discovered with photographs. Telescopes did not capture a glowing wall of galaxies proclaiming their domain. The boundary is invisible. The cosmos hides its architecture in motion, not shape. You measure where galaxies are going, and the truth reveals itself. Scientists followed the arrows. The paths didn't spread outward like fireworks. They converged like migrating birds. Multiple superclusters, once thought independent, were revealed as organs of a larger body. The Hydra Centaurus region, the Norma cluster, the Great Attractor, all pieces of a single continent of gravity. Maps failed, vocabulary failed, even cosmology itself hesitated. If a galaxy belongs to Laniakea, it is not because it sits inside a bubble of stars. It is because it will never escape the pull. Give it enough time, hundreds of millions of years, and it will drift inward, swallowed by the same gravitational sea. The boundary is not a wall. It is a horizon of destiny. When the research team unveiled the structure, they refused to name it after themselves, or after a Latin phrase polished in academic marble. They looked to a culture that understands the feeling of standing beneath infinite sky. Hawaiian navigators crossed oceans with no land in sight. They steered by stars. They trusted invisible currents. The universe has its own currents. Laniakea carries that idea forward. Immeasurable heavens. Not unreachable heavens, not unknowable. Simply too vast to fit in a single human thought. You could cross this supercluster for 500 million light-years and never reach its edge. If the Milky Way were the size of a grain of sand, Laniakea would span continents. Every human civilization that has ever existed, every story, every war, every dream, compressed into a fleck of cosmic dust drifting in a gravitational river older than Earth. The name is not poetry. It is precision. We do not live in a galaxy. We live in an immeasurable heaven, and we are falling through it. For decades, we thought galaxies formed tidy clusters like beads on string. Laniakea shattered that idea. Galaxies do not merely cluster, they belong to enormous basins of attraction, regions where gravity directs their motion across hundreds of millions of light years. The word cluster once made us feel safe. It sounded local, contained, manageable, a city of galaxies surrounded by cosmic countryside. You could put boundaries around it, measure it, study it, like a zoologist observing a herd. But nature is never that simple. When astronomers traced the flows of thousands of galaxies, they found that clusters are not cities. They are neighborhoods in a sprawling empire whose borders stretch farther than the imagination can comfortably hold. A galaxy cluster is born when matter collapses inward. Stars, gas, and dark matter tangled together until gravity squeezes them into a dense knot. Tens of thousands of galaxies may orbit that knot in a convulsing dance of collision and cannibalism. Scientists once thought these knots were islands. Their gravity, their contents, their reach, self-contained. The universe, according to that model, was an archipelago of these islands, separated by vast gulfs of empty darkness. But the darkness is not empty, and the islands are not islands. Clusters join filaments, threads of matter stretching like veins across the cosmic web. Filaments join walls. Walls create highways of gravitational potential. Entire regions of space become sloped like bowls, and galaxies slide along those slopes whether they want to or not. Even the largest clusters are not gravitational sovereigns. They are tributaries feeding into deeper, older, larger currents. The shock came when astronomers followed those currents to their endpoints. Instead of finding multiple independent destinations, they found one. Not a destination defined by brightness or beauty, but by motion. The question was not, where does a galaxy sit? The question was, where will it go? The answer was staggering. Some clusters were not pulling matter toward themselves, they were being dragged. Their galaxies flowed like snowmelt toward a vast gravitational ocean. The Hydra Centaurus region, the Norma cluster, the local group, all sliding along the same invisible slope. Their individual identities dissolved when seen at scale, the way the Amazon River is not 100 streams, but one unstoppable system. This is why Laniakea is not simply another supercluster. It is a redefinition. Its borders are not walls of matter, but watersheds. Imagine the universe as a landscape painted with gravity. Every particle, every star, every galaxy is a drop of rain falling toward the lowest point in the terrain. The boundary between two superclusters is not a fence, it is a ridgeline. Step one atom over that ridge, and its future changes forever. Clusters that once looked autonomous, giant empires of tens of thousands of galaxies, are revealed to be provinces of a single realm. Their gravitational fields, once thought dominant, are merely eddies within a far deeper current. They do not grow in isolation. They are sculpted, stretched, and oriented by forces that span 500 million light-years. We believed the cosmos was made of clusters. We were wrong. It is made of flows. And those flows answer to masters older and larger than anything we can see with our eyes. Our Milky Way, Andromeda, and dozens of dwarf galaxies form the local group. A drifting island only 10 million light-years wide, a tiny raft caught in the slow tide of something far larger. It sounds enormous when spoken aloud. 10 million light-years. Enough distance to swallow every star you've ever seen and all the worlds yet undiscovered. Yet in the architecture of the universe, the local group is microscopic. Imagine a speck of dust floating in the atmosphere above the ocean. That is our home, not the ocean itself, not even a drop of salt water, just the dust. A handful of galaxies bound together by shared gravity and shared fate, trying to stay coherent as the cosmic tide pulls endlessly around them. Two giants dominate this raft, the Milky Way and Andromeda, sister spirals locked in slow-motion gravitational embrace. They orbit a shared center of mass, each tracing an invisible arc through intergalactic space. Every second, Andromeda draws closer, not by meters, not by miles, by entire stars of distance. 200 kilometers every second, faster than any rocket humanity could dream of building. Around these two giants swarmed dozens of faint companions. Dwarf galaxies, irregular fragments, stellar debris suspended by dark matter halos like insects hovering around wolves. Some of these dwarfs are so dim that Earth's telescopes only discovered them in the past decade. Others are ghost-like, their stars stretched thin by tidal forces, half-eaten remnants of ancient collisions long forgotten. The local group is not pristine. It is not a cradle. It is the aftermath of billions of years of violence. We once believed this was the universe, that our small island was a representative example of how galaxies arrange themselves. A neat cluster, bounded by empty space, sitting politely in the cosmos. Then astronomers began to look outward, not at what the local group contained, but at how it moved. The revelation was unsettling. The local group was not sitting still. It was gliding across the void like a raft on a black ocean, carried by currents stretching far beyond its borders. Where do these currents flow? They do not point toward the center of the Milky Way. They do not point toward Andromeda. They point outward, toward something invisible, a larger structure, a gravitational well so wide that even the combined mass of two giant galaxies cannot resist. Our local group is not the captain. It is a passenger. This is where scale becomes incomprehensible. The Milky Way holds 100-400 billion stars. Andromeda holds nearly 1 trillion. Yet together, they are merely a seed at the edge of a far larger gravitational garden. The local group drifts not toward one galaxy, but toward a collection of galaxy clusters thousands of times larger than itself. drawn like iron filings toward a magnet buried beneath cosmic mist. The ocean does not care about the raft. Currents pull, gravity whispers, and the local group follows. To see Laniakea, scientists trace the cosmic web, filaments stretching like neural networks across space, linking galaxy clusters the way synapses link living minds. Most people picture the universe as an explosion, galaxies blasting outward into a featureless void, expanding into nothingness like sparks from a dying fire. This image is comforting, simple, linear, but it is wrong. The cosmos is not a uniform cloud of stars. It is a woven structure. Vast strands of matter stretch across unimaginable distances, forming threads, sheets, and junctions. Together, they resemble something eerily familiar, the branching pathways of a living brain. These filaments are not thin roads of dust. They are highways of galaxies, each hundreds of millions of light-years long. Each bright cluster is a metropolis, tens of thousands of galaxies packed together. Between them, glowing in faint intervals, are the roads. Dimmer galaxies, drifting in long chains, pulled into alignment by the gravity of dark matter. Follow these chains long enough, and they twist, intersect, and merge at colossal knots where superclusters gather. This web did not appear after the universe matured. It grew from the very beginning. In the first fractions of a second after the Big Bang, the newborn universe was not perfectly smooth. Quantum fluctuations, tiny wrinkles in the energy field, created slightly denser regions. 1 part in 100,000 was enough. Gravity amplified the difference. Denser regions pulled in more matter, becoming denser still. Sparse regions lost their material, becoming hollower. Over billions of years, the universe stratified itself like a river sorting sediment. The filaments thickened, the voids widened, structure emerged. Every filament you see today is a record of the universe's own memory. It is the fossilized trajectory of gravitational collapse. Those threads of matter are not temporary. They are the pathways along which galaxies formed, migrated, and collided. Our local group sits on one of these strands, like a bead threaded into the cosmic tapestry. Somewhere behind us, galaxies stream toward the Virgo cluster. Somewhere ahead, they flow toward Hydra Centaurus. The filament does not ask their permission. It simply pulls. Scientists visualize this structure by measuring redshifts, tiny shifts in the wavelength of light arriving from distant galaxies. Like police radar tracking speeding cars, redshift reveals velocity, moving toward us, moving away, or drifting sideways through space. When millions of measurements are plotted together in 3 dimensions, the universe lights up like circuitry. The web comes into focus. Thick junctions mark superclusters. Thin tendrils mark connective tissue. Open voids appear as black oceans where matter simply never gathered. The scale defies human intuition. A single filament can be longer than the distance from the Milky Way to Andromeda, multiplied by 1,000. A void between filaments can be so empty that an entire galaxy could drift through it for 1 billion years and never encounter another. These empty regions are not mistakes. They are the spaces where gravity lost the battle. Structure forms where matter wins. Laniakea is not a dot on the web. It is one of its largest knots, a mind of galaxies, fed by filaments that stretch across the darkness like cosmic nerves. We cannot photograph the supercluster directly. We map it the way sailors once mapped ocean currents, by watching how galaxies drift, pulled by distant forces they never see. This is the great paradox of cosmic cartography. The universe is full of structures so vast that their boundaries vanish into silence. A galaxy cluster shines brightly enough to burn its shape into our telescopes. A supernova screams its existence across millions of light years. But a supercluster like Laniakea whispers. It reveals itself only through motion, not snapshots, not images. Instead, through trajectories written over millions of years. Imagine standing on a beach, staring at a black ocean in the dead of night. You cannot see the currents, you cannot trace the tide. But if you drop lanterns into the water, and watch where they drift, you eventually learn the rules of that unseen sea. Galaxies are our lanterns. They shine for billions of years, their light carrying direction, speed, and distance. We do not see the current itself, only how it drags them. Astronomers began with redshift, the slight stretching of light as galaxies move away from us with the expansion of space. Redshift is the universe's clock. It tells us how far away something is and how quickly it recedes. But the problem is subtle. Redshift measures expansion, not motion relative to gravity. And galaxies do not move in perfect obedience to expansion. Some drift sideways, some fall inward, others surge outward against the universal tide. These deviations are called peculiar velocities. Small, almost fragile distortions, yet they are the fingerprints of hidden giants. They are how we know a gravitational empire exists beyond the horizon of our telescopes. To isolate these deviations, scientists gathered thousands of galaxies, each one a glowing buoy, and measured not just their distance, but their direction of travel. They plotted arrows in every corner of the sky. At first, the picture was noise, random scatter. Then, a pattern emerged. The arrows curved. Not once, not twice, but everywhere. Like leaves caught in the same wind, entire clusters bent toward the same coordinates. This was the first outline of Laniakea. What they mapped was not matter, but influence. The pull of an unseen basin spreading across hundreds of millions of light years. Galaxies inside the basin drifted inward. Galaxies beyond it drifted away. And the boundary was sharp, not in light, but in motion. Where the arrows flipped direction, the supercluster ended. Mapping this required more than observational courage. It required abandoning the way astronomy had been practiced for a century. No more counting galaxies. No more catalogues of brightness. They had to think like geologists, examining erosion, like biologists tracking migration. Gravity was the landscape. Galaxies were the herd. And slowly, layer by layer, the invisible coastline emerged. Nothing in the cosmos looked like the neat islands we once imagined. The local group was not a pebble. Virgo was not a mountain. They were foothills on the slope of a continent so large that its existence had been hiding in plain sight. We did not photograph Laniakea. We listened to the paths of galaxies and let their motion draw the map. Galaxies do not simply ride along with cosmic expansion. Some surge forward or fall backward against the universal tide. These peculiar velocities reveal hidden gravity in the dark. To understand why this matters, you must first understand the rule they are breaking. The fabric of the universe stretches in every direction. Space itself expands, not because galaxies push outward, but because the distance between them increases as the cosmic fabric inflates. Imagine dots drawn on a balloon. As you blow air into it, every dot gets farther from every other dot. Not because they're moving on their own, but because the rubber beneath them stretches. That is the Hubble flow. The universal drift that should dominate on large scales. But galaxies are stubborn. Some refuse to obey the pure expansion. They accelerate toward regions of unseen mass. Others stall, resisting the cosmic pull like swimmers caught in an undertow. These deviations are not mistakes. They are messages, signals whispered through motion. A peculiar velocity is the part of a galaxy's speed that expansion cannot explain. If Hubble expansion says it should be moving away from us at 1,200 kilometers per second, but we measure 1,500, that extra 300 is not random. That is gravity reaching across unimaginable distances, bending the galaxy's path like a hand dragging a compass needle. Imagine seeing hundreds of galaxies bending toward the same invisible location. Imagine realizing that the source is not a single galaxy, not a cluster, but a gravitational bruise smeared across millions of light years. Peculiar velocity is the clue that something bigger lurks in the dark, mass that does not glow, structures that cannot be seen, forces that sculpt the universe beyond human sight. Each measurement is a tiny rebellion against cosmic order. A galaxy might speed ahead of the expansion, accelerating like a ship caught in a hidden current. Another might slow down, resisting motion, tugged toward a distant mass concentration. When astronomers plotted these anomalies on three-dimensional maps, the data behaved like iron filings dropped around a magnet. They curved, they clustered, they aligned. Peculiar velocities unified the universe in motion. Suddenly, clusters that looked independent were shown to be in transit. The Virgo cluster was not a gravitational endpoint, it was a waypoint. Hydra Centaurus was not an isolated kingdom. It was downstream in a river of stars. The local group, with its giants Andromeda and the Milky Way, was not sitting still in space. It was accelerating towards something far greater than itself. These velocities cut through the illusion of static galactic neighborhoods. They showed us the universe not as a star chart, but as a weather map. Fronts, currents, pressure gradients, invisible to the eye, obvious only when wind bends the grass. For decades, cosmology assumed that expansion was the dominant force. They revealed the fingerprints of dark matter halos, the gravitational imprint of filaments, the influence of objects so massive they warp the trajectory of galaxies millions of light years away. And when the flow vectors converged, they pointed toward one thing: a supercluster whose pull was strong enough to bend entire regions of the cosmos, a destination that would eventually be named Laniakea. Scientists realized galaxies behave like raindrops on mountains. They fall toward different valleys, separated by ridgelines of gravity. Those valleys define the borders of superclusters. This was the breakthrough that rewrote cosmology. We had built our maps around brightness, counting galaxies, cataloging clusters, tracing where the stars were. But matter alone is not the terrain of the universe. Motion is. Just as water is shaped not by soil but by slope, galaxies are shaped not by their positions but by the gravitational contours of space-time. A raindrop may land only a meter away from another, yet the two will flow to entirely different seas if the mountain between them tilts their paths in opposite directions. The cosmos is built on the same principle. In this analogy, galaxy clusters are not lakes. They are basins, collectors of motion. Gravity carves invisible channels through space, directing entire populations of galaxies towards specific destinations. A supercluster is not an object at rest. It is a gravitational valley. And the borders between superclusters are not physical walls or sheets of galaxies. They are watersheds. They mark the point where the direction of cosmic flow flips. Picture yourself at the crest of a great divide. Rain falling to your left will feed one ocean. Rain falling to your right will join another. Nothing separates the raindrops except geometry, an imperceptible change in slope beneath your feet. The boundary is invisible, but it controls the destiny of millions of drops. Replace raindrops with galaxies, replace mountains with gravitational topography, and you understand what Laniakea is. To identify these watersheds, scientists charted peculiar velocities and traced every galaxy's course, not at this instant, but over cosmic time. They asked a simple question. If the universe stopped expanding today, where would each galaxy move? Faint dwarfs and titanic spirals alike have eventual homes written into their paths. When the answers were plotted, the cosmos sorted itself. Galaxies that would ultimately fall toward Virgo belonged to one basin. Galaxies headed toward Perseus Pisces belonged to another. Where those futures diverged, there was a ridge. These ridgelines were not small. They stretched across hundreds of millions of light years. They cut right through the largest known structures, slicing past clusters that once looked unified, separating them into different gravitational kingdoms. Even enormous chains of galaxies could fall on opposite slopes of the same divide. One cluster might drain toward the great Attractor. Another, only a little farther out, would slip into the basin of the Shapley Supercluster. Mapped by matter, they seemed connected. Mapped by destiny, they were strangers. This is the moment superclusters became alive. They were no longer static piles of galaxies. They were dynamic systems defined by flow. You are not a resident of the local group because you live here now. You are a resident of Laniakea because your galaxy, along with 100,000 others, will inevitably plunge toward the same gravitational heart. Cosmic watersheds don't care about what exists today. They care about what the universe will become. At the heart of Laniakea lies a gravitational vortex known as the Great Attractor, a region dense enough to tug entire galaxy groups toward it, bending their trajectories like fish caught in a net. The name sounds dramatic, almost mythic, but scientists did not choose it for poetry. They chose it because nothing else fit. When astronomers traced peculiar velocities across millions of light years, the arrows converged toward one point in the sky, not a bright galaxy cluster, not a black hole visible in X-ray glare, just a region of space thick with gravity. A silent whirlpool, a cosmic undertow pulling galaxies inward as if the universe itself were leaning in one direction. The disturbing part came quickly. We cannot see it clearly. The Great Attractor sits behind the galactic plane, hidden behind thick clouds of dust and stars in the Milky Way. Our own galaxy blinds us to the gravitational monster stalking us in the dark. The region is shrouded in what astronomers call the zone of avoidance, a strip of sky where starlight and dust block our view like heavy fog blocking a coastline. The sky looks empty there, but the data say otherwise. For decades, telescopes stared into this blank region with infrared eyes, radio eyes, X-ray eyes, trying to catch a glimpse of the beast. They found fragments, clusters, filaments, hints of massive structures tucked behind our stellar curtain. Hydra, Centaurus, Norma, pieces of a larger tapestry, but the tapestry itself refused to show its full shape. The gravity was unmistakable. The source was hidden. Imagine a deep ocean current pulling at ships, drowning fleets, rearranging coastlines, and the sailors never seeing the wave that does it. That is the Great Attractor. Entire galaxy groups, like ours, drift toward it at over 1,000 kilometers per second. The local group tilts, the Virgo cluster bows. The Centaurus region accelerates. They are all being dragged into a gravitational whirlpool larger than anything we can see. Scientists once believed the Great Attractor was the Norma cluster, a concentration of galaxies nearly 200 million light-years away. For a brief moment, the mystery seemed solved. Then deeper surveys shattered that comfort. The pull did not end at Norma. It continued. Stronger, broader. Like discovering the shoreline was not the island, but the edge of a continent. Behind the Great Attractor lies the Shapley concentration, a galaxy cluster so massive that it may be the true culprit, a luminous mountain of matter whose gravity reaches across 500 million light-years. The attractor may not be a point at all, but a slope, a cliff, part of a long descent into a deeper gravitational basin. And we are already sliding down that slope. We are not falling alone. Over 100,000 galaxies, spirals, ellipticals, dwarfs, giants are drifting toward the same invisible nexus. They do not know each other. They will never meet. Yet they share a future, bound by the same pull. The Great Attractor is not a predator stalking us. It is the center of a basin we cannot escape, a gravitational truth hidden behind the dust of our own galaxy, and we are already in its tide. Farther still, an even more massive node lurks, the Shapley concentration, a luminous continent of galaxies whose mass distorts the entire region like a stone warping the fabric of a trampoline. If the Great Attractor is a whirlpool, Shapley is the ocean floor beneath it, the deeper basin toward which everything eventually drains. Astronomers first noticed its presence not through sight, but through excessive motion. Galaxies hurtled in its direction faster than the Great Attractor alone could explain. Every vector that should have slowed near the Norma region instead sharpened, as if some greater gravitational force lay beyond, waiting in the distance like a second horizon. Shapley is not subtle. It is one of the largest mass concentrations in the local universe, over 8,000 galaxies densely packed into a sprawling lattice of clusters. If Hydra Centaurus is a metropolis, Shapley is an entire continent, lit by billions of stars. It sits nearly 650 million light-years away, a distance so enormous that light we see from it tonight departed when complex life on Earth had not yet learned to breathe air. The structure glows like a torch in deep space. But its light is not why it matters. What defines Shapley is gravity, the invisible weight that bends the trajectories of galaxies over cosmic timescales. Like a boulder dropped onto stretched fabric, it depresses the surrounding space-time. Clusters fall toward it. Filaments bend around it. Even the Great Attractor sits downstream from it, an intermediate eddy in a larger flow. To grasp Shapley's influence, imagine the universe as a vast valley. Smaller basins gather water, streams converge, rivers form. But far below them lies a single drain. Every tributary ultimately empties there. Shapley is that drain. Everything around it is shaped by its existence, whether galaxies are aware of it or not. Even our local group, trillions of kilometers away, is caught in the ripple, tilted by the gravitational slope Shapley created. And yet, Shapley is not a single structure. It is an empire of clusters interlocked in a brutal gravitational pact. Galaxies in its core collide, merge, and cannibalize one another. Smaller clusters orbit like moons around planets, drawn inward and torn apart. Dark matter cocoons these formations, binding them with an unseen skeleton. The light from stars is a decoration. Gravity is the body. We once imagined superclusters as static, islands of galaxies sitting peacefully in cosmic night. Shapley annihilated that illusion. It is not an island, it is a whirlpool of motion, a continental shelf of mass that dictates the futures of regions hundreds of millions of light-years across. Its pull is not dramatic in the human sense. There is no sudden collapse, no cataclysm. Its violence is slow, operating on timescales that reduce civilizations to sparks against the dark. This is why Laniakea is not just a cluster of clusters. It is a gravitational basin defined by flow. The hierarchy of gravity does not end at the scale of galaxies. It stretches upward, endlessly recursive, until our minds fail. You and every star you've ever seen are part of that hierarchy, drifting, accelerating, falling, toward a luminous continent that has never heard our name. The question burned for decades. How big is Laniakea? How far does its influence extend? The answer required redefining what size even means for structures made of millions of galaxies. At first, astronomers tried the traditional approach. Count the galaxies, map the clusters, draw borders where density falls below a threshold. It failed instantly. Laniakea doesn't end where galaxies become sparse. It doesn't respect brightness, or shape, or the faint edges of a telescope's view. Like fog over mountains, its boundary is invisible, present only in the direction galaxies move. Size, as we normally understand it, has no meaning here. A human can measure a forest by its trees. A galaxy can be measured by its stars. But how do you measure a basin of gravity? How do you chart the slope of space-time itself? You cannot photograph it. You cannot point a camera at the sky and say, "There." That is where it ends. The structure is too large, too slow, too dim. Its borders exist only as futures. A galaxy belongs to Laniakea not because it is near, or bright, or visually connected, but because, given infinite time, it will fall inward. The metric is not distance, it is destiny. And destiny had to be calculated. Scientists used a map called the Cosmic Flows dataset, vast catalogues of galaxy velocities woven together like strands of DNA. Instead of asking where galaxies were, they asked where they were going. Each galaxy was given a velocity vector, its movement through space relative to expansion. These vectors formed patterns. Entire galaxy groups flowed toward Virgo, others bent in longer arcs toward Hydra Centaurus, still more pointed toward Norma and beyond. Thousands of arrows converged, crossing clusters and bridges of matter, as if the universe itself were leaning in a single direction. That convergence was Laniakea. To isolate it, researchers used a mathematical technique called basin of attraction mapping. They simulated the flow of matter backward in time, tracing each galaxy uphill against gravity until the paths reached the same point of motion. Like raindrops traced to the crest of a hill, all the lines ended on the same watershed. That watershed lay between superclusters. On one side, galaxies drained toward the Great Attractor and ultimately Shapley. On the other, they flowed toward Perseus Pisces. The ridge between them was the boundary of Laniakea. When the calculation was complete, the result stunned even the scientists who performed it. Laniakea spans roughly 520 million light-years, 520 million, an expanse so large that even light, racing at cosmic speed, would take more than 500 million years to cross it. Within that space lie about 100,000 galaxies, each one with its own history, its own suns, its own worlds, its own chance at sentience. And yet all of them are passengers on a single current. Try to grasp the scale. If the Milky Way were a single grain of sand, Laniakea would stretch across continents. Every star you know, every planet you have ever imagined, every story humans have ever told, compressed into a dust mote, drifting in a gravitational valley older than Earth itself. The universe does not measure greatness by mass or brightness. It measures it by the direction your galaxy falls. By tracking over 160,000 galaxies and their motions, scientists discovered streams converging toward the same destination, revealing Laniakea as a cosmic basin of flow. This was not a handful of measurements from a narrow patch of sky. It was a survey on a scale that had never been attempted. Galaxies catalogued not by brightness or shape, but by trajectory. Each galaxy became a point in a slow-motion river that had been flowing for billions of years. When the researchers plotted these points and their vectors, the sky transformed. What once looked like scattered jewels became a migrating herd. The universe did not just expand, it drifted. Imagine standing above the Amazon basin, watching every droplet of rainfall, every rivulet, every tributary. Eventually you would see the truth. They all plunge into a single river, a central artery so large it becomes inevitable. Laniakea is the cosmic Amazon. The galaxies are the raindrops. Their paths trace the boundaries of a basin so vast that only their collective motion reveals its shape. The dataset was called Cosmic Flows. Instead of telling astronomers where galaxies were, it told them where they were going. It tracked distance, velocity, and deviations from Hubble expansion, peculiar velocities that act like currents beneath the surface of an expanding sea. Every galaxy was an arrow. Some pointed gently inward. Others curved sharply, pulled like minnows toward a dark depth. A few resisted, drifting at odd angles like debris caught on the edge of a whirlpool. But none of them moved randomly. The most haunting realization came from the scale of agreement. A dwarf galaxy 80 million light-years from us bent toward the same direction as massive clusters 300 million light-years farther out. Objects separated by hundreds of millions of light-years, too far apart to influence one another, still shared a destination. Their motions echoed like voices humming the same low note through the void. When astronomers rendered these flows in 3 dimensions, the visual was shocking. Thin filaments of galaxies funneled from every corner of the local universe toward a gravitational heart. Branches merged, streams thickened. The map grew denser until all motion coalesced into a single downward slope, the Great Attractor and ultimately the Shapley concentration beyond it. Laniakea was not a structure defined by walls. It was a whirlpool defined by consensus. It is difficult to convey how alien this realization was. For decades, cosmology treated galaxy groups as isolated kingdoms. A supercluster was a collection of matter surrounded by emptiness, but this view turned the universe into a frozen photograph. The Cosmic Flows map replaced the photograph with a time-lapse. Matter moved. Gravity sculpted. Galaxies obeyed the terrain. Clusters no longer looked like monoliths, they looked like traffic intersections. Even more unsettling, the flows ignored distance. Proximity no longer defined belonging. A galaxy could be far away yet still be part of Laniakea because its motion bent toward the same gravitational center. Borders became fluid, membership became a trajectory, fate replaced geography. 160,000 galaxies became lines on a single canvas. and every line whispered the same truth. We are not stationary. We are not isolated. We are drifting together into the same cosmic river. Gravity works slowly at these scales. A galaxy 400 million light-years away still feels the whisper of the Great Attractor, like a distant lighthouse guiding ships across a quiet ocean. In the human world, gravity is immediate. Drop a stone, and it falls. Step off a ledge, and the ground finds you. But gravity does not need to be quick to be absolute. In the deep cosmos, its influence stretches across distances so vast that light itself grows tired on the journey. A galaxy does not sprint toward its destiny. It drifts, altering its path by fractions of a kilometer per second, decade after decade, until billions of years have passed, and it has traveled farther than every civilization that will ever exist. This slow pull is what astronomers call gravitational memory. The universe remembers where mass once was. A cluster that collapsed hundreds of millions of years ago still exerts influence today. The gravity of long-dead stars and galaxies swallowed into larger bodies continues to shape the flow. Space does not forget. It bears the imprint of every concentration of matter like a bruise on stretched skin, and galaxies respond to those bruises long after the original actor has vanished. Imagine a ship at sea. The waves it once cut through remain long after it has disappeared beyond the horizon. The water never truly returns to stillness. Ripples propagate outward, intersect, shift the surface. Gravity behaves the same way. The Great Attractor may not appear dramatic in photographs. It is not a blazing quasar or a black hole devouring matter in real time. Yet, its presence warps the trajectories of entire galaxy clusters, shaping paths across distances so large the mind instinctively recoils. Even more curious, the influence is cumulative. A galaxy does not feel gravity from a single source. It is tugged by thousands. A filament pulls it one way. The Virgo cluster tugs another. The Shapley concentration weighs on it like a distant mountain pulling rivers toward its slope. A galaxy's true course is not a simple arrow. It is the sum of gravitational memories stretching across cosmic history. Every event that occurred in the past bends space in the present. This is why the precise mapping of Laniakea was so revelatory. When researchers traced motion vectors backward, they were not simply identifying where galaxies are going. They were revealing where gravity has been working for billions of years. They turned time inside out, peeling back the influence of dead stars, collapsed clusters, and ancient mergers that left their fingerprints etched into the curvature of space-time. And this memory travels far. The Milky Way, tiny on the canvas of the supercluster, feels the pull of structures we will never see with the naked eye. A galaxy farther away, 300 or 400 million light-years distant, feels the same pull. It is not influenced by proximity. It is influenced by inevitability. Like iron dust responding to the ghost field of a magnet buried beneath cloth, we are used to thinking of gravity as force. But at these scales, it becomes destiny. A galaxy does not sprint. It leans. It waits. And then, over eons, it obeys. Superclusters are not walls of matter. They are boundaries of motion. A galaxy belongs to Laniakea if it eventually falls inward rather than drifting outward forever. This is the rule that shattered our old maps. We once believed structures were defined by brightness and population. Draw a circle around clusters and filaments, count their suns, declare a region. But the universe cares nothing for our categories. Size is not imposed by what we can see. It is carved by gravity. Borders are invisible thresholds where motion changes direction, where fate diverges. If a galaxy crosses that line, it is not merely outside Laniakea, it has escaped its future. Imagine two raindrops falling on opposite sides of a mountain ridge. They may land only meters apart, but one will travel to the Pacific, the other to the Atlantic. Their trajectories diverge, not because they are different fluids, but because the terrain beneath them slopes in opposite directions. Superclusters are built on similar ridgelines. One slope leads toward the Great Attractor and into the deeper pull of Shapley. The other leads elsewhere, toward Perseus Pisces, toward different gravitational centers and different cosmic destinies. That ridgeline is the border of escape. For Laniakea, it passes through the sculptor wall, slices between massive filaments, and cuts entire clusters in half. A galaxy on one side of the divide will, eventually, even against the universe's expansion, fall toward the basin of the Great Attractor. A galaxy just beyond the boundary will drift away forever, pulled instead by distant structures that do not belong to Laniakea at all. To find this border, scientists had to stop thinking like astronomers and start thinking like hydrologists. They traced peculiar velocities backward against the cosmic slope, hunting for the point where flow lines diverged. Every galaxy was assigned an origin basin, the gravitational valley it would roll into if time were infinite and expansion were fixed. If its path curved inward, it belonged to Laniakea. If it bent outward, it was already beyond escape. The beauty and the terror is that this boundary is not static. Expansion stretches space even as gravity tugs inward. The two forces compete everywhere. In dense regions full of galaxies and dark matter, gravity wins. In the vast voids, expansion dominates. Superclusters exist precisely at the knife's edge where these powers meet. Their borders are not physical walls, they are dynamic equilibrium lines, forever shifting, forever tested by the push and pull of the universe itself. And like everything in the cosmos, even escape is relative. A galaxy just outside the boundary may drift slowly outward now, only to be redirected by tidal forces of some distant mass that has yet to form. The universe is a sculptor still carving its masterpiece. The ridgelines we draw are true only for this moment. But today, the map is clear. We know which galaxies fall inward and which drift away. We know the slope of space-time in our local universe, and we know that the Milky Way, the local group, and nearly 100,000 other galaxies are on the downward side of the ridge. We are not fleeing, we are descending, and there is no turning back. Imagine standing where gravitational pull changes direction. A boundary where galaxies on one side flow toward one attractor and on the other side toward another. That is the edge of Laniakea. Scientists call this boundary a dividing surface of flow, but the phrase does not capture its true strangeness. This is not a physical wall of stars or dust. There is no curtain of light marking the transition. Instead, the boundary is written into the motion of galaxies, an invisible equator, a gravitational frontier that splits the universe into enormous domains of influence. If a galaxy crosses it, its destiny changes forever. It is like stepping across the crest of a mountain. One step, and every drop of rain flows toward a different ocean. When researchers mapped the peculiar velocity field, the subtle deviations from cosmic expansion, they noticed a region where the arrows flipped direction. Galaxies that had appeared to flow toward the Great Attractor suddenly diverged, bending toward a completely different structure, the Perseus-Pisces Supercluster. No emptiness, just a change in the direction of motion. Imagine a surfer riding a wave. For miles, the current pulls toward shore, until suddenly a rip current takes over, dragging outward with equal force. Nothing has changed in the water's color or smell, but the underlying motion has shifted. That shift defines the boundary. The cosmic equator is that moment on a universal scale where attraction reverses its allegiance. To find it, astronomers had to retrace every galaxy's journey backwards through time. It was not enough to know where a galaxy currently sits. That is only a snapshot, a single frame in a movie that has been playing for 13.8 billion years. What matters is the direction of the story. Where does the galaxy want to go? Where will it end up if given infinite time? When you pull on that thread long enough, the cosmic tapestry reveals its seams. Those seams form a vast partition. On one side, the galaxies destined for the Great Attractor and the deeper gravitational well of the Shapley concentration. On the other, galaxies drifting toward Perseus-Pisces and structures even farther beyond. These two regions do not mingle. They are gravitational nations. Their members may brush past one another, share filaments, even pass through the same void, but they do not share a future. The place where their paths diverge is the cosmic equator. What makes this boundary unsettling is its subtlety. Within a cluster, the gravitational gradient is strong and obvious. Galaxies fall inward like pebbles sliding down a slope. But at the scale of superclusters, the gradient is ghostly. The slope is measured not in kilometers per second, but in tiny perturbations layered over the Hubble expansion. A galaxy might drift for 500 million years before its true allegiance becomes clear. Yet the moment it crosses the equator, its path is locked. Humanity has always sought borders, coastlines, mountains, rivers. We expect boundaries to be visible. The cosmos does not care about our instincts. Its borders are written in motion, not light. You do not see the cosmic equator. You feel it in the way galaxies lean. Stand on one side, and you are falling toward the heart of Laniakea. Stand on the other, and you are gone, drifting into another universe of gravity entirely. Closer to home lies the Virgo cluster, the anchor of our local group. 10,000 galaxies swirl in its grip, a glowing jewel of gravitational stability within the greater storm. In a universe where gravity often feels like a distant whisper, Virgo is a shout. It is the nearest major cluster to the Milky Way, a sphere of mass so concentrated that even at 50 million light-years away, its pull bends the trajectories of entire galaxy groups. Virgo is not just a collection of galaxies, it is a gravitational lighthouse, a bright core that the surrounding filaments orient themselves around, a silent command center deep in the cosmic web. Picture Virgo as a glowing heart suspended in darkness. Around it orbit spirals and ellipticals, each galaxy containing billions of suns, pulled into a slow dance lasting billions of years. The galaxies do not move chaotically. They circle, collide, merge, and settle, like planets around a star, except every planet here is a city of stars, and every merger is an extinction-level event. Virgo is messy. It is hungry. It is alive. Most clusters are dominated by a few heavyweights, but Virgo has an emperor. Messier 87, a supergiant elliptical galaxy with a supermassive black hole at its core so enormous that its shadow was the first ever photographed. In astronomical images, M87 looks calm, a soft blur of gold. In truth, it is a cosmic predator. Its black hole devours stars, gas, and entire galaxies that stray too close, ejecting relativistic jets thousands of light-years long. It is the furnace at the center of a cathedral of violence. Yet for us, Virgo is safety. Not in a human sense, but in a cosmic one. It stabilizes the local group. Our Milky Way and Andromeda, together with dozens of smaller galaxies, are not drifting alone in emptiness. They are falling toward Virgo, like beads sliding down a slope of space-time. The gravitational basin funnels everything within 60 million light-years toward this central node. We will not reach it for billions of years, but our trajectory is already fixed. Virgo is one of the reasons we know the universe is not random. If galaxies moved by chance, their velocities would scatter in every direction. Instead, their motions point inward. They lean toward Virgo, like trees bent permanently by prevailing wind. Even the galaxies on the margins feel the whisper of the cluster's dark matter halo, 1,000,000 trillion solar masses of invisible scaffolding shaping their fates. The cluster sits near the center of the larger Virgo Supercluster, which was once thought to be the ultimate scale of structure. For decades, astronomers believed this region, hundreds of millions of light-years wide, represented the upper limit of galactic organization. Virgo, impressive as it is, turned out to be a tributary of something even larger. Its motion is not autonomous. It is being pulled, slowly, inevitably, into the gravitational descent that defines Laniakea. Imagine that. A cluster containing 10,000 galaxies, each galaxy containing billions of suns, is not the destination. It is only the beginning of the fall. Virgo is our anchor, yes, but it anchors us to the current, not to the shore. Galaxies do not move randomly through space. They trace graceful arcs through the voids, like fireflies following unseen wind currents. From our tiny vantage point on Earth, the night sky feels static. Stars look frozen. Constellations never change. Even galaxies, those spirals of 100 billion suns, appear unmoving, pinned to the darkness like beads on velvet. But this is an illusion born of limited time and limited scale. Step back far enough, and the truth becomes impossible to ignore. Galaxies drift like schools of glowing fish migrating through a cosmic sea, their paths bent by forces so vast that the human brain struggles to comprehend them. Every galaxy is a lantern in motion. Some glide through voids, tracing elegant arcs that stretch for hundreds of millions of light years. Others travel the filaments, sliding along gravitational highways that connect clusters like bridges between continents. Their movement is slow, infinitesimal when measured in human years, yet unstoppable across cosmic epochs. A galaxy may move only a few hundred kilometers per second, but over hundreds of millions of years, that becomes a journey longer than everything ever recorded in human history. Astronomers see this motion not with their eyes, but with the fingerprints embedded in starlight. A galaxy moving away from us subtly reddens, its wavelength stretched like taffy. A galaxy falling sideways or inward skews its spectrum in other ways. Combine thousands of these measurements, and the sky becomes a field of arrows. Each arrow points to a future. Each arrow reveals a destination. The universe, once thought to be a cloud of static lights, becomes a network of travelers, each one pulled by invisible gravity toward ancient basins. It is the voids that make these motions most visible. Contrary to their name, voids are not nothing. They are immense regions of underdensity, cosmic deserts where matter is scarce and gravity is weak. Here, galaxies do not collide. They drift, and because nothing slows them, their trajectories become pure expressions of gravitational influence. If you were to release 100 lanterns into a black wind, they would drift with it, not in straight lines, but in smooth curves aligned with the currents. They are fireflies in the night, carried by the breath of space-time. These arcs are not random flourish. They trace the outlines of the cosmic web. Each path is a signature of the forces beneath. When galaxies bend toward Virgo, we see the local slope of the gravitational landscape. When they fall toward Hydra Centaurus, we witness deeper curvature. And when their streams continue still farther, cohering around Shapley, the deepest basin of all, we understand that our cosmic neighborhood is not a handful of clusters. It is a river system feeding a continental drain. Nothing in the universe truly stands still, not suns, not galaxies, not light itself. Everything flows, everything leans. Across distances so vast that human words begin to fail, galaxies are quietly changing places, slipping across invisible gradients, one photon at a time. If you could look at the universe with the patience of eternity, you would not see constellations. You would see currents of light migrating through darkness, each one following a path carved long before any star was born. When scientists mapped these flows, they found the structure's outer limit, where galaxies no longer drift inward. Beyond that boundary, they belong to a different gravitational nation. It was not a visual edge. There was no halo of light or sudden void marking a change. Instead, the threshold revealed itself through motion. Galaxies on one side curved gently toward the basin of Laniakea, as if sliding down a sloped valley. On the other side, their trajectories bent away, like raindrops falling off a roof in the opposite direction. The cosmos did not divide itself by mass or shape or brightness. It divided itself by fate. The place where that fate changes is the Laniakea threshold. To trace it, astronomers had to follow streams of movement, not static positions. They charted galaxy after galaxy, thousands at a time, plotting the direction each would take if the universe stopped expanding and gravity was allowed to complete its work. Imagine pausing time, stars frozen mid-burn, clusters suspended like ash in a still atmosphere. and then asking a single question. The answer split the universe into territories. One territory flowed inward, toward Virgo, Hydra Centaurus, and ultimately the deeper well of the Shapley concentration. This was Laniakea. The other region flowed away, toward Perseus Pisces and its own great attractors, following entirely different filaments and gravitational highways. These cosmic nations shared no border guards, no walls, no light. The only difference was direction. To stand at that boundary, if one could, would be to witness a quiet war of influence. On one side, galaxies lean like trees bent by wind. On the other, they arc the opposite way. A drift of millions of suns, each larger than our imagination, determined by the gentle tug of unseeable masses. The threshold is not a political border with flags and bells. It is a gravitational ridge, the highest point between two cosmic watersheds. Laniakea's boundary is clearest around the sculptor wall, a vast structure where galaxies align and flow like travelers converging toward a valley. At first glance, the region looks unified. Clusters connected by filaments, bright strings of matter stretching across hundreds of millions of light-years. But beneath the surface lies a fracture. Push each galaxy's projected motion forward millions of years, and the illusion dissolves. Some will drift toward Virgo, others will escape toward Perseus Pisces, never to return. That moment of divergence is the threshold. Humans instinctively think in terms of objects, where things are, what they contain. But Laniakea forced astronomers to adopt a different instinct, where things are going. It turned the universe from a static painting into a flowing continent of migration. A galaxy's membership is not a function of its address, but of its destiny. If the Milky Way were just outside that boundary, the story of our universe would be completely different. Our measurements of expansion, our interpretation of dark energy, our sense of place, everything. But we are on the inner slope. We belong to the basin. Just as rivers do not argue with gravity, galaxies do not negotiate their future. They simply drift, and the threshold marks who we are and who we can never become. Laniakea spans 520 million light-years. If the Milky Way were a single grain of sand, Laniakea would be a continent. Human language fractures under that scale. We are not designed to grasp distances that exceed the lifespan of stars. A light-year is not a poetic metaphor. It is a unit of physical travel. It is the distance a beam of light, racing at the fastest speed allowed by the universe, crosses in a single year. Multiply that by 500 million, and you begin to approach the true span of this gravitational basin. Not a city of galaxies, not a country, a continental plate of matter bending the fabric of space. When you stand beneath the night sky, you see a handful of stars. The brightest few thousand sprinkle themselves across your vision like scattered sparks. Our galaxy alone contains hundreds of billions of them, and yet it dissolves into insignificance when placed beside its home supercluster. The Milky Way is a fleck of dust drifting in a storm of galactic continents. Laniakea holds nearly 100,000 galaxies, and each of those galaxies holds its own billions of suns. If you attempted to cross this supercluster in a spacecraft, you would die. Your descendants would die, and their descendants would die. Every civilization your species could evolve would collapse into myth before the journey was halfway done. Even photons, the ghosts of the universe, struggle. Light leaving one edge of Laniakea tonight will not reach the other side until Earth's continents have rearranged, oceans have emptied, and whatever species calls our planet home is long gone or unrecognizable. And yet, this structure is not solid. It is mostly void. Empty expanses dwarf the populated filaments. In some directions, you could travel for 1 billion years without hitting a single galaxy. The emptiness does not mean failure or absence. It is the natural consequence of how matter behaved after the Big Bang. Minute fluctuations in density were amplified by time, gravity flowing toward the richest pockets and abandoning the poor ones. It is the cosmic equivalent of mountains and ocean basins. The filaments are ridgelines, the voids are seas. Think about what that means. Whole superclusters can drift through these oceans of emptiness and never touch. They are so far apart that even their mutual gravity is a whisper. Our home is not surrounded by neighbors. It floats in an archipelago of unseen islands. And still, Laniakea is not the largest structure in the universe. It is one continent among many. Beyond it lie other empires of galaxies, some even more massive, some barely charted. The deepest gravitational wells remain hidden behind dust, distance, and the limits of our instruments. Cosmology is not finished. Every map we draw is provisional. Every measurement is incomplete. You are not inside a galaxy. You are inside a basin of flow, 500 million light-years wide, drifting toward a gravitational center you will never see. The scale does not ask for your belief. It simply exists, silent and indifferent, waiting for you to understand how small you truly are. Motion within the supercluster is glacial. Galaxies spend billions of years migrating inward, drawn by a pull they can never outrun. To human eyes, nothing appears to move. The Milky Way hangs in the night sky like a painting, serene and eternal. Stars seem nailed in place, constellations frozen across lifetimes. We evolved on a planet where change happens in seconds, minutes, or at most a few generations. Gravity at the scale of Laniakea does not care about such timescales. It is slow in a way that makes mountains seem reckless and continents impatient. The forces shaping this supercluster operate on epochs, not centuries. Motion happens in whispers, not storms. A galaxy does not tumble into the gravitational basin like a rock rolling downhill. It sinks. It drifts. It adjusts its course by fractions of a kilometer per second, every second, for millions upon millions of years. Each nudge slightly alters its path, bending it ever closer to the valley floor of space-time. No individual star feels the change, no planet senses the turn. A galaxy is too large, its inhabitants too small, to perceive the slope beneath it. Only when astronomers compare hundreds of millions of light-years of motion does the direction become clear. Imagine a glacier moving across a landscape. To someone standing beside it, it is still, unmoving. But return after centuries, and the world is different. Valleys carved, boulders displaced, forests gone. Gravity in Laniakea is the glacier. Galaxies are the stones caught inside it, carried slowly toward a destination they never chose. They do not accelerate like meteors diving toward Earth. They simply lean and lean and lean across cosmic time. It is tempting to think of these motions as gentle or peaceful. They are not. They are inevitable. A galaxy cannot protest. It cannot change its trajectory once it has committed to the flow. All that matters is mass. The Virgo cluster pulls, Hydra Centaurus pulls harder, the Great Attractor pulls harder still. And behind them waits Shapley, the gravitational abyss into which the entire region drains. The patience of gravity is not kindness, it is triumph. Human beings like to imagine agency, as if stars and galaxies could choose their paths. But the universe is blunt. A galaxy might resist for 1 billion years, riding the expansion of space, drifting sideways across a filament. Then a slightly denser region tugs a little harder. The galaxy bends, almost imperceptibly. 100 million years pass. It bends again. It is not a negotiation. It is the end of a long argument solved by mass. Think about how long 1 billion years truly is. Earth formed 4.5 billion years ago. For half of that time, the planet was nothing but molten stone and shallow oceans. Human history is a sliver at the edge of that timeline. And yet galaxies require billions of years just to shift their trajectories a few degrees. The journey to the core of Laniakea will outlast our species, our star, and likely the habitability of every world we know. That is the gravity of patience, a force that never rushes, never relents, and always wins. Clusters form islands, filaments form bridges, voids form oceans. Laniakea is not one thing, it is a geography of gravity laid across the dark. This is the image that finally reshaped our understanding of the universe. We had been looking for walls, borders, and clusters, as if the cosmos were built from solid shapes. Instead, its structure resembles a scattered archipelago, a chain of continents separated by vast, silent seas. Each galaxy cluster is a landmass. Each filament is a narrow land bridge, fragile yet essential, and every void between them is a deep, black ocean where almost nothing exists. The islands seem isolated at first. Virgo, Norma, Hydra Centaurus, each luminous and self-contained, like cities of light surrounded by darkness. But zoom out, and the separation dissolves. Filaments tie these islands together, the way coral reefs stitch one island to another beneath the surface. Matter flows along these filaments, funneled by invisible dark matter scaffolding that cuts through the void like underwater mountain ridges. Galaxies travel these paths because there is nowhere else to go. Imagine a map of the Pacific. Islands float across a blue expanse: Hawaii, Tahiti, Samoa, each distinct, yet part of a larger region shaped by tides and ocean currents. The islands do not know they are connected, they simply exist. But the ocean tells the truth. It binds them, transports them, carries everything that lives or dies upon it. Laniakea is the same. Its clusters are islands. Its voids are oceans. Its filaments are the unseen trade winds that connect everything, even across hundreds of millions of light years. These bridges are not thin or fragile. They can contain thousands of galaxies stretched into chains so long that light from one end will not reach the other before a new species evolves, thrives, and goes extinct. A filament might extend for 500 million light-years, twisting through space like a vein in a living organism. Where filaments intersect, clusters form, the way deltas form at river mouths. The density increases, matter collapses inward, star formation accelerates, and new galaxies spark into existence. The voids between them are more intimidating than the islands themselves. They are not empty like a vacuum chamber. They are less. Starlight rarely crosses them. Gravity barely stirs. No new structures form there because there is nothing to gather. These are the deserts of the cosmos, inhospitable expanses, where the expansion of space is the only dominant force. If a galaxy drifts too far into a void, it does not find neighbors or filaments, it finds exile. This geography was not planned. It is the fossil imprint of the universe unfolding from its earliest moments. Minute fluctuations in density during inflation became hills and hollows in space-time. Over billions of years, gravity amplified the hollows into voids and the hills into filaments and clusters. Laniakea is not a single island or a single empire. It is a continent chain rising from the sea of the universe, shaped not by whim but by physics itself. Human maps are drawn on paper. The universe draws its maps in motion. Every galaxy is a traveler in this archipelago, carried along by tides older than starlight. We look up and see a sky full of scattered pearls. But when the currents are revealed, the pearls become a net, stretched across a cosmic ocean we are only beginning to understand. One of Laniakea's boundaries runs along the sculptor wall, a ridge of galaxies whose alignment marks where cosmic flows diverge. It is not a wall in any human sense. There is no barrier, no gleaming fence in the void. The sculptor wall is a gravitational ridge, a towering topographic rise in the landscape of space-time. To the eye, it looks like a broad ribbon of galaxies arcing across hundreds of millions of light-years. But motion reveals its true nature. On one side, galaxies lean toward the Great Attractor, their trajectories bending inward like leaves drawn into a vortex. On the other side, they peel away, migrating toward distant gravitational realms that lie far beyond Laniakea. The ridge is not physical, it is directional. For years, astronomers struggled to understand the sculptor wall. It appeared as a simple corridor of galaxies, a filament like many others. No one suspected it was a watershed. Only when velocity maps were plotted did its importance emerge. Peculiar velocities, the subtle deviations from the universe's expansion, flipped along this structure. Galaxies below the ridge flowed in one direction. those above it flowed in another. The sculptor wall turned out to be a cosmic watershed line, the crest that separates gravitational kingdoms. To appreciate the scale, imagine the Appalachian Mountains bisecting a continent. Rain falling on one slope eventually reaches the Atlantic. Rain on the other side travels to the Gulf of Mexico. The ridge does not care how close the drops land to each other. It cares only about direction. That is how the sculptor wall works. Two galaxies, separated by only a few million light-years, might live very different futures. One will slide toward the Great Attractor basin. The other will escape down a different slope and vanish into Perseus-Pisces space. The galaxies anchored to the wall itself are like trees rooted along a ridgeline. They are tall, luminous, often clustered, their light marking the boundary in a way no human engineer ever could. Some are spirals stretching their arms into the void. Others are elliptical giants, bloated by eons of mergers, drifting without haste. They do not know they are part of a border. Their stars burn all the same, but the path of their motion gives away the truth. This boundary unsettles because it reveals how little visual appearance matters. To the naked eye, or even to telescopes, the sculptor wall looks like part of Laniakea. Galaxies sit beside one another, sharing filaments, sharing neighbors, sharing the same cosmic web. But destiny ignores proximity. A galaxy's membership is not decided by where it sits, but by the direction it will ultimately travel. The sculptor wall marks the point where those journeys fork. It is one of the clearest demonstrations of a principle that shattered traditional cosmology. Superclusters are not objects. They are not islands. They are not static sacks of galaxies. They are basins of motion, sculpted by the interplay of gravity and expansion across billions of years. The wall reveals the seam between those basins. It is one of Laniakea's outer ribs, the place where its gravitational skin folds back and gives way to another domain. Stand on one side, and the galaxies fall inward. Stand on the other, and they drift away forever. The sculptor wall does not shout its existence. It only tilts the future. Like a second river running uphill, the Perseus-Pisces Supercluster pulls galaxies in the opposite direction, forming a rival current beyond Laniakea's reach. At first glance, it feels like a contradiction. How can one region of the universe pull galaxies inward while another pulls them outward? Shouldn't the cosmos have a single gravitational center, like water drawn to the lowest point in a valley? The truth is, stranger. There is no single valley. The universe is carved into multiple basins, each with its own gravitational destiny. Laniakea is one of them, Perseus-Pisces is another, and between them runs a fault line. A cosmic border where the direction of motion flips like a compass needle crossing into another magnetic field. Perseus-Pisces is enormous. It is a chain of galaxy clusters stretching more than 300 million light-years, snaking across the darkness in a great arc. Unlike Laniakea, which forms a broad basin, Perseus-Pisces is narrow and elongated, like a mountain range rising above a plain. It is dense enough to bend the flow of thousands of galaxies, pulling them along its length. Instead of descending toward a single central point, galaxies here travel laterally, sliding through its filament like marbles rolling down a gutter. What makes it remarkable is the way it opposes Laniakea. On one side of the sculptor wall, galaxies drift inward, surrendering to the pull of Virgo and the Great Attractor. On the other, they turn away. They fall toward Perseus-Pisces, sliding along filaments that run counter to the Laniakea current. To a cosmologist watching this from above, it would look like two massive rivers flowing toward different oceans, separated only by a ridge of gravitational terrain. The galaxies have no consciousness, no will, no knowledge of their neighbors, and yet their motions carry the memory of their basin, the imprint of unseen mass sculpted billions of years ago. This counterflow is essential to understanding the cosmic web. Without it, we would still imagine superclusters as walls or bubbles, a set of isolated structures floating in a void. Perseus-Pisces shows us that superclusters are not isolated at all. They are competitors. Their influence stretches across hundreds of millions of light-years, tugging at galaxies like rival kingdoms. Laniakea does not own every region around it. Where its pull weakens, Perseus Pisces strengthens. Where one basin drains inward, the other drains away. Motion, not location, determines loyalty. If you could stand between the two flows, the scene would be surreal. Galaxies on your left would drift toward the southwestern sky, into Virgo and the deeper gravity of Hydra Centaurus. Galaxies on your right would lean northeast, toward the elongated arc of Perseus Pisces. Nothing would mark the line physically. No glowing bridge, no dark curtain, only motion, subtle and unstoppable. There would be no sound, no wind, no shifting color. You would feel nothing. And yet the fate of entire clusters would be written beneath your feet. Perseus Pisces reminds us that Laniakea is not the universe's center. It is merely one gravitational nation among many. Its borders are finite. Its reach has limits. Outside them, other empires rule, drawing their own galaxies along ancient paths. The cosmos is not a monarchy. It is a world of currents, each one sovereign in its domain. And somewhere in the space between, galaxies decide nothing. They simply fall to the side that pulls hardest. At its center, Laniakea is not violent. It is quiet, a slow gravitational convergence zone where time moves on billion-year scales. It is easy to imagine the universe as a battlefield of collisions, explosions, and catastrophic mergers. We learn about supernovae tearing stars apart, black holes devouring everything in reach, and galaxies slamming together in bursts of fire and debris. But the true core of a supercluster is none of those things. It is not a storm. It is not chaos. It is a still harbor where motion is steady, inevitable, and calm. The center of Laniakea is not a furnace. It is a slope worn down by ages of gravity, where every galaxy glides like a feather descending through still air. The violence happens on the outskirts. At the edges of the basin, clusters tear smaller galaxies apart. Filaments stretch them thin, stir their gas, and feed new star formation in brief bursts of brilliance. But this turbulence dissipates as one approaches the gravitational center. The speed differential shrinks, trajectories flatten, interactions become fewer. It is not that the core is empty, it is simply settled. The debris has already been consumed. The cannibalism is finished. What remains are the survivors, great elliptical giants, ancient spirals stripped of gas, and clusters whose histories are carved not in explosions, but in the quiet erasure of orbital energy. If you could watch the region in accelerated time, the story would look like sedimentation. Galaxies fall inward, movements slow, and then they drift in ever smaller spirals, smoothing into the basin like sand settling at the bottom of a river. Every one of them is responding to a gravitational shape carved long ago. The great attractor does not pull with violence, it pulls with inevitability. It is a slope, not a claw. This slow collapse is how gravity wins. Not by sudden force, but by patience. The galaxies have no choice. They do not see the end of their path, and they do not need to. Their orbits decay imperceptibly, each million-year period shaving a fraction of velocity, each billion-year epoch tightening their arc. The inhabitants of those galaxies, if any exist, would never sense their motion. They would see stars rise and fall, seasons pass, continents drift, species emerge and vanish, and yet their entire civilization would be hurtling toward the heart of Laniakea, so slowly that not one will live to witness even a single, meaningful tick of the journey. At certain scales, stillness is indistinguishable from motion. That is the cosmic secret. The calm center appears frozen only because human lives are too short to perceive movement. In truth, everything is gliding inward. Everything is leaning toward the same basin. The clusters that dominate the outer regions will eventually join the quiet. Virgo will slow, Hydra Centaurus will flatten. Even Shapley, that luminous continent of galaxies, may one day descend toward a larger basin beyond our current knowledge. There is no final resting place. only a deeper slope hidden by time. The heart of Laniakea teaches a humbling lesson. Not everything powerful needs to roar. Some forces conquer by being the place all others eventually come to rest. The universe speaks in explosions, yes, but its greatest structures whisper. They move with the patience of gravity, drawing galaxies into the calm fold of collapse, 1 billion years at a time. Our Milky Way is not sitting still, it is on a journey, a curved path, tens of millions of light years long, pulling us toward the Virgo cluster, like iron filings to a magnet. From inside a galaxy, the world feels motionless. The sun rises, the planets orbit, stars remain pinned to their constellations for thousands of years. But this stillness is an illusion created by time too short and distances too small. The Milky Way, along with its retinue of dwarf companions, is gliding through the fabric of space at hundreds of kilometers per second, moving along a path it never chose, toward a destination older than life on Earth. We are not drifting randomly. Peculiar velocities, those deviations from the pure expansion of the universe, reveal our trajectory. The local group, the small island of galaxies we inhabit, is being drawn toward Virgo along subtle gravitational contours that stretch across the darkness like currents beneath an ocean surface. It is not a straight line. No galaxy travels in a straight line. The universe is filled with invisible slopes, tiny ridges of dark matter, eddies formed by clusters and filaments. We drift along them the way a fallen leaf follows the bends of a river. This journey began long before the Milky Way resembled anything we recognize today. Even as our galaxy was assembling from clouds of gas in the early universe, attraction toward Virgo already whispered through the void. The gravitational field sculpted by that massive cluster did not wait for stars to form. It acted upon proto-galaxies, upon dark matter itself, long before any planet was warmed by a sun. In this sense, our destination predates our existence. The path was carved before there was anyone to trace it. On this journey, the scale becomes impossible to humanize. The Milky Way will not reach Virgo in 1 billion years, or even 10. The timescale involved is like the slow drift of continents multiplied by millions. Stars will be born and die. Earth may freeze under a dying sun, or be swallowed when the sun expands. Humanity, if it survives at all, will evolve beyond anything recognizable. All of this will happen while our galaxy has traveled barely a fraction of the way. Even the motion of Andromeda, our nearest major neighbor, is part of this transit. The collision that awaits us, 3 to 5 billion years in the future, is not a standalone event. It is a step along the path to Virgo. The two galaxies are like droplets merging into a larger stream, their individual histories dissolving into a shared destination. When their spiral arms tear each other apart, when new stars bloom in tidal bridges of gas, when their cores settle into a single giant elliptical, the merged system will continue the same slow fall, still one of many travelers in the basin of Laniakea. Humans imagine galaxies as monarchs, proud and independent. But every galaxy is a passenger. The Milky Way is no exception. We orbit a black hole at our center. We orbit alongside dwarf galaxies. We orbit through filaments we will never see. And all the while, we are being pulled, not with violence, but with the patient insistence of a force as old as time. Galaxies are not fixed jewels adorning the universe. They are ships, and we are aboard one. The sea is space-time, the wind is gravity. And the voyage will outlast everything we know. Galaxies that cross Laniakea's ridge cannot return. Their trajectories bend forever inward. They have become citizens of the Supercluster. There is no ceremony. No cosmic announcement marks the moment of entry. A galaxy does not flare or dim or leave a trail of light behind it. It simply crosses an invisible slope, like a droplet of rain passing the crest of a roof. The next, its path tilts toward one side of the universe instead of the other. The change is irreversible. What determines membership in Laniakea is not where a galaxy sits, but where it will go. Once its motion turns inward, destiny has taken hold. The pull is subtle at first, Gravity works gently at scales this large, nudging a galaxy by fractions of speed each million years. That is enough. A tiny shift becomes a curve becomes a spiral. Even a line that bends by 1 degree will drift into a new future given enough time. Motion in the universe behaves like weather. Winds do not need to howl to reshape a continent's climate. They need only persist. Crossing the ridge of Laniakea is not an act of arrival. It no longer participates in the open tide of the universe. It has handed itself over to the valley of gravity. From that moment, expansion becomes secondary, and the faint backward tug of matter becomes the law of its existence. Astrophysicists call this the basin of attraction, but the phrase is too sterile. A better word is belonging. To understand why return is impossible, imagine a marble rolling across a shallow slope. Once it falls over the edge of a bowl, the shape of the terrain dictates its fate. The marble cannot climb back up on its own. It continues downward, orbiting the bottom, slowing, settling. Now, replace the marble with a galaxy, the bowl with millions of light years of warped space-time, and the slope with the gravitational influence of hundreds of thousands of galaxies. Crossing the rim is not the end of a journey. It is the beginning. Galaxies often cross the ridge quietly. They may drift in from filaments, pulled along like ships guided by undersea currents. Others approach with speed, dropped into the basin after interactions with neighboring clusters. Still others are born already inside, their stars igniting within streams that point toward Virgo or Hydra Centaurus from the instant gas collapses into their first suns. They become Laniakean before they even know themselves as galaxies. The ridge is not a barrier that keeps objects out. It is a frontier that decides what they will become. A galaxy on the outside may roam for billions of years, carried by expansion, trading neighbors, skimming voids, tracing long arcs across the cosmic web. It may still orbit, it may still collide, it may still grow, but every step is oriented toward the gravitational heart of the supercluster, whether that heart lies in Virgo, the great attractor, or the deeper draw of Shapley. There is a quiet beauty in this inevitability. It means that the universe, in all its chaos, keeps certain promises. Motion becomes destiny not in a single instant, but in a million small decisions made by gravity. Stars do not know their paths. Civilizations have no idea they are drifting, but the galaxies know, not in thought, but in motion. Once you lean toward Laniakea, the universe has already claimed you. The journey is long, but the ending is certain. Even as gravity draws galaxies together, the universe expands around them. Laniakea is both collapsing and being stretched, an impossible paradox that somehow holds true. It sounds contradictory at first glance. How can the Milky Way, Virgo, Hydra Centaurus, and Shapley be slowly falling toward one another while the space between them grows larger every second? It is because we often imagine the universe in human terms, as a solid thing, or a single event happening in a single direction. In reality, two processes shape the cosmos at once. Gravity pulls inward. Expansion pushes outward. Neither cancels the other. They coexist like opposing winds, carving patterns that stretch across billions of light years. If the universe contained only gravity, everything would collapse. Every cluster would sink into larger clusters. Every galaxy would end in monstrous mergers, spiraling down into central supermassive black holes until the night sky was nothing but heat and ruin. But the universe has expansion, born from the Big Bang and accelerated by dark energy. It spreads space outward like dough rising in an oven, pushing galaxies apart unless gravity is strong enough to resist. The boundary between these effects is delicate. Inside a galaxy cluster, expansion is meaningless. The cluster is gravitationally bound. The galaxies orbit one another, tugged by the mass of stars, gas, and dark matter. Their individual motions overpower cosmic expansion. But outside clusters, in the immense cosmic voids, expansion dominates. There, galaxies drift away from each other effortlessly, like boats on an ocean as the tide recedes. They do not collide. They do not fall inward. They float, separated by millions of light years and destined never to meet. Laniakea lives between these regimes. It is a basin of attraction in a universe that is otherwise drifting apart. Think of a river basin carved in an expanding landscape. Mountains erode under the force of rain, and water still flows downhill, even as the continent beneath them is carried away on tectonic plates. Gravity does not stop just because the ground stretches. It simply works within the terrain available to it. Laniakea is that terrain, a gravitational valley nested within cosmic expansion, its galaxies sliding inward even as the fabric of space itself balloons outward. This duality reveals something profound. The scale on which gravity wins determines the scale of structure. Small scales are ruled by gravity, solar systems, galaxies, clusters. Medium scales are complicated, superclusters like Laniakea, where gravity and expansion compete. Large scales are unquestionably ruled by expansion. Beyond the basins lies the domain of dark energy, where no mass concentration is strong enough to pull galaxies back together. If the Milky Way were just a little farther from Virgo, or if the mass of Hydra Centaurus were slightly lower, the local group might not be bound at all. It would drift outward with the rest of the cosmic tide, lost to the emptiness forever. Our galaxy belongs to Laniakea, not because of proximity, but because gravity there is still strong enough to overcome expansion, barely, delicately, persistently. This is why Laniakea seems impossible. Its collapse is not dramatic. It is invisible, inaudible, glacial. The galaxies do not crash or rush inward. They lean toward one another over hundreds of millions of years, like dust settling in a room. Meanwhile, the cosmic fabric beneath them stretches farther apart. The valley deepens while the mountains around it rise. The basin gathers in a universe trying to tear itself open. It is a balance so strange that the human mind instinctively rejects it. But the universe is not concerned with our instincts. It allows both truths to exist, galaxies falling inward and space expanding outward. Laniakea breathes in and out at the same time, collapsing into its heart while the cosmos itself continues to unfurl. The map of the universe changed the day Laniakea's borders were drawn. Superclusters faded into illusions. Only flows mattered. Before that moment, astronomers believed they understood the cosmic landscape. They drew borders around bright regions, counted galaxies, labeled clusters, and assigned names to enormous patches of sky. Virgo Supercluster, Hydra Centaurus, Coma. They treated these formations the way ancient maritime cartographers treated continents. Draw a coastline, decorate the interior, and pretend the map is truth. But the universe does not respect the borders we draw. The day Laniakea was defined, the idea of static superclusters collapsed. The revelation was simple and devastating. Structures are defined by motion, not by shape. It does not matter how many galaxies sit in a region. It does not matter how they look. What matters is the direction they flow. If a galaxy is drawn toward the great Attractor and the deeper basin downslope from it, then it belongs to Laniakea. If it leans toward Perseus Pisces or toward some distant filament, then it does not. Visual maps became irrelevant overnight. Every galaxy in the sky had to be reclassified not by where it was, but by where it was going. This transformation echoed through astronomy like a quiet earthquake. It reshaped the catalogue of the nearest universe. What looked like separate realms merged into one. Hydra Centaurus, once thought independent, became an arm of Laniakea. The Norma cluster, mysterious and partially veiled by the Milky Way, revealed itself as a gate toward the deeper flow into Shapley. The Virgo cluster, which for decades had been treated as the gravitational capital of our region, was demoted from emperor to anchor, one important stop in a much larger descent. Even the concept of belonging changed. Galaxies that lived beside each other, sharing filaments and neighbors, sometimes turned out to belong to different gravitational nations. Two galaxies separated by only a few million light-years could drift in opposite future directions, like two raindrops landing on opposite sides of a mountain ridge, destined for different oceans. The map of the cosmos shifted from a static diagram to a dynamic weather system. The implications run deeper than cartography. For most of the history of astronomy, the universe was imagined as a mosaic. Isolated islands of galaxies separated by voids. Superclusters were boundaries, not processes. But Laniakea forced scientists to think in 4 dimensions. Space and motion became inseparable. Structure was no longer a frozen sculpture. It was a living flow, shaped by ancient gravity and guided by the deep contours of dark matter. This realization also exposed how much we still do not know. If Laniakea is defined by gravitational flows, what defines the flows themselves? Why do some basins form and not others? How stable are these borders? Will the cosmic geography change again as expansion accelerates? Even now, astronomers suspect that Laniakea is not permanent. As dark energy continues to stretch the universe, gravitational basins may fracture. The currents we see today may eventually thin into separate streams, scattering galaxies into isolation. And yet, for a moment in cosmic time, we have clarity. We know where we live. We know the slope beneath us. The universe is no longer a map of dots. It is a migration, a river system of galaxies flowing through the dark. We are not residents of the Virgo Supercluster. We are part of Laniakea, a continent of gravity hidden in the stars, revealed only by the direction everything moves. Our galaxy is part of a caravan, tens of thousands of galaxies all moving toward one gravitational center, each unaware of the others, like travelers lost in a fog. Imagine flying above a desert at night. Countless people walk across the sand, each carrying a lantern. Their paths look random, their footsteps scattered, but watch long enough, and a pattern appears. Even without communicating, they drift in the same direction, guided by something they cannot see. That is Laniakea. Our Milky Way is one lantern among many. A tiny spark drifting through a darkness shaped by forces older than time itself. Galaxies do not know about one another. They do not communicate. They are not aware of their shared motion. A spiral in Hydra Centaurus has no knowledge of the Milky Way. The glowing ellipticals of Centaurus A do not know about the dwarfs trailing Andromeda, yet they all lean toward the same gravitational center, pulled like iron filings scattered across a sheet of paper. It is a silent march, an unspoken migration that binds the local universe together. This is what makes Laniakea awe-inspiring. It is not merely a cluster of matter, it is a choreography. Gravity bends the trajectories of galaxies that have never touched and never will. They may be separated by hundreds of millions of light years. Their stars may form and die. Civilizations may rise and vanish, and none of it matters. They are united by the slope of space-time. The universe bends beneath them, and they follow. This drift is not fast. It is not dramatic. You could live 1,000 lifetimes and never see measurable progress. The Milky Way creeps toward Virgo at roughly 600 kilometers per second, but against a backdrop of 500 million light years, that pace is glacial. Galaxies move like continents do, barely perceptible from inside, relentless from afar. Over millions of years, their paths become rivers. Over billions, their rivers become basins. Picture thousands of shipwrecked vessels carried by unseen currents. Each captain believes the voyage is solitary, the wind unpredictable. But from above, a cartographer sees the truth. Every vessel is drifting toward the same harbor. The galaxies of Laniakea are those vessels. Some are ancient giants, stripped of their gas, elliptical hulks swollen from eons of mergers. Others are small and fragile, dim dwarfs with only a few million stars. All are passengers on the same ocean. And yet, the drift is not uniform. It twists and bends through filaments, past voids and alongside clusters. The path is influenced by dark matter halos, local clusters, and long threads of gas and dust. The journey is complex, like a river delta fed by countless tributaries. But no tributary escapes the slope. Every stream eventually finds the same sea. To us, this motion feels meaningless. We are too small, too brief, We live and die on a rock that has not even crossed a single pixel of its intergalactic path. It does not rush, it does not negotiate, it simply bends matter until everything finds its place. We are not alone in our drift. We never were. We share our journey with galaxies we will never see, never hear, never know, all of us falling together toward the same distant heart in the dark. At the periphery of Laniakea lie galaxies that will never reach the core. They are too far, trapped between expansion and attraction, drifting forever. These are the castaways of the cosmic sea, the galaxies that hover at the threshold of the basin but never cross it. Their motion is angled just so, balanced delicately between the inward pull of gravity and the outward swell of cosmic expansion. They are like boats caught in a slow tide. The waves push them shoreward, but the undertow pulls them back, leaving them adrift in the shallows. They simply exist beside it, close enough to feel its pull, but not close enough to surrender to it. The reason is not dramatic, it is mathematical. Gravity weakens with distance, its influence fading like the whisper of a voice across an empty hall. Expansion, however, does not weaken. It accelerates. The farther a galaxy sits from the basin, the stronger the outward stretch of space-time becomes. At some point, the two forces reach equilibrium. The gravitational slope of Laniakea becomes too shallow to drag the galaxy inward, and the quiet expansion of the universe takes control. The galaxy is released, not into freedom, but into timeless drift. These edge galaxies are among the loneliest objects in the cosmos. They may have formed in filaments like all the others, tethered by faint gravitational bridges, but over billions of years, the filaments stretch and thin, the bridges snap, their neighbors drift inward, carried by denser masses, leaving the edge galaxies stranded. What remains around them is emptiness, deep cosmic voids where few stars ignite and no clusters grow. These galaxies drift along the void's perimeter, half aware of the basin's direction, but never able to join the caravan. Their futures are different from ours. The Milky Way is destined to collide with Andromeda, merge into a giant elliptical, and eventually descend toward Virgo. Edge galaxies may never experience such encounters. Their paths are gentle arcs that slowly flatten into straight lines as expansion takes over. Their stars dim without being replenished by mergers or fresh gas. Over trillions of years, they become fading ghosts, massive halos of dark matter wrapped around red embers, remnants of a universe that once lit itself in fire. Scientists have traced some of these trajectories. They are the galaxies whose peculiar velocities barely bend inward. They flirt with the Laniakea boundary but do not cross it. A small change in mass might have tipped them into the basin. A single merger in the distant past might have provided enough momentum, but it never came. The universe does not care how close the drop of rain lands to the ridge, 1 centimeter to the left or right, and its destiny is written. These edge cases remind us that cosmic geography is unforgiving. There is no mercy in the flow. Gravity does not reward proximity or effort. It rewards commitment. A galaxy must fall decisively toward the basin to belong to it. Anything less, and its fate is isolation. Imagine a traveler wandering through mist, following the faint glow of lanterns in the distance. The trail narrows, the lanterns drift away, and soon the traveler is alone. The road continues, but the caravan is gone. They have not turned back. They have simply passed beyond reach. So it is with the galaxies at the edge of Laniakea. They drift in the outskirts of a gravitational empire they will never join. Close enough to feel the pull, far enough to escape it. Citizens of no supercluster, inhabitants of the cosmic frontier, forever moving, forever alone. What happens when a basin of this size collapses? Does it form a megacluster? A supermassive black hole? Or something beyond our imagination? Gravity is patient, and patience always wins. Eventually, the galaxies falling into Laniakea will meet. They will merge, grind, consume, ignite, and fade. Clusters will become larger clusters. Superclusters will become something else entirely. But nothing in our current textbooks tells us what lies at the end of a process this enormous. We have no simulation that spans the trillions of years necessary to watch a structure this vast reach its final form. We are staring into a future that will never belong to us, and asking what shape eternity takes. We can extrapolate from smaller scales. When galaxies collide, they merge into elliptical giants, swollen and star-poor. The gas that fuels starbirth is burned or flung outward. When clusters collide, the result is a furnace of dark matter, plasma, and violent shocks stretching across millions of light years. They produce arcs of X-ray radiation, invisible to the human eye, but glowing like lightning storms through our telescopes. Extrapolate upward, and we might imagine superclusters doing the same thing, merging into megastructures so massive that the word cluster becomes meaningless. But gravity behaves differently as scale increases. When objects reach a certain size, they stop merging and start collapsing. They fall inward, not as separate parts, but as a whole. Their individual identities blur, their internal motions freeze. The result is a gravitational monolith, a region of space-time warped so deeply that nothing escapes its pull. At galactic scales, this process births supermassive black holes. At the scale of Laniakea, we have no precedent. No simulation has ever convincingly shown what happens when hundreds of thousands of galaxies descend into a single slope. One possibility is a hypercluster, a colossal elliptical structure, millions of galaxies wide, so starved of gas that it glows only faintly. Such an object would not resemble the starry spirals that dominate the universe today. It would be a husk, a red mass of dying suns, slowly drifting toward thermal death. Another possibility is more dramatic. The structure collapses inward until even light cannot escape. A black hole not the size of a galaxy, but the size of a supercluster, a singularity with the mass of tens of trillions of stars. A tear in space-time large enough to swallow everything around it. There is also a third option, something we do not yet have the physics to describe. Our equations break at boundaries. They fail at singularities. They waver when dark energy and gravity compete over unimaginably long stretches of time. Perhaps Laniakea never collapses fully. Perhaps acceleration from dark energy outruns gravity before the final merger completes. Perhaps the supercluster stretches apart, fragmenting into smaller islands that drift forever, each one a burning relic of what once could have been. We stand on a planet orbiting a single star, inside a small galaxy, at the edge of a vast basin of motion. Our tools are extraordinary, our equations powerful, our simulations immense, and still we cannot see far enough ahead to know what becomes of a continent of galaxies that falls in on itself. We do not know if the universe ends in hunger or in silence. We do not know if gravity finishes the work or if expansion tears it away first. We trace the flows. We map the borders. We stand on the slope of Laniakea and look inward, and we wait for a future no human mind will ever witness. Every night sky you have ever seen, every star, every galaxy glimmering faintly, belongs to this vast unseen continent. We are citizens of Laniakea, drifting slowly home. It is easy to forget this when we stand outside and look upward. The stars seem local, personal, immediate. A dome of pinpricks that hangs over our homes, our cities, our childhoods, but that sky is not a ceiling. It is a window into a landscape so immense that our words break under its weight. Those faint specks of starlight are not scattered randomly, they are outposts of a gravitational nation, signs of our membership in a structure beyond all human architecture. The Milky Way is only one voice in a choir of galaxies humming along the same gravitational gradient. Even Andromeda, often imagined as our great cosmic rival, is nothing more than another passenger on the same slow descent. Together we slide across intergalactic space, weaving through filaments like threads drawn into the same loom. The Virgo cluster is our first great destination on this journey. The great Attractor is the slope beyond it, and Shapley waits deeper still, silent and ancient, a mountain whose gravity shapes the entire region. We did not choose this path. Our galaxy did not petition the universe for citizenship. We became part of Laniakea long before the sun ignited, long before atoms on Earth assembled into the molecules that would become forests and oceans and eyes that stare at the stars. The basin claimed us in the early expansion, when matter first pooled around the densest places. We do not steer our galaxy, we ride it, carried through the void like leaves on an unseen river. Standing beneath the night sky, you might not feel the motion at all. That is because gravity works with the patience of stone. Our galaxy moves at hundreds of kilometers per second, and yet the stars around us look frozen. Their lives span billions of years. They flare and fade while we live for a handful of days in cosmic time. We mistake stillness for stasis. But if you could play the universe in fast forward, galaxies would stream through space like flocks of birds migrating across the heavens. Humans have always looked upward, searching for gods, for meaning, for messages scribbled on the canvas of night. The truth, once discovered, is stranger and quieter. We are part of an enormous flow, a gravitational migration spanning 500 million light-years. There are no instructions, no prophecy, no purpose carved into the stars. Every landscape on Earth ends somewhere. Every ocean has a shore. Even the sky has limits. But Laniakea stretches beyond imagination. Its borders are drawn not in light, but in destiny. The galaxies on our side fall inward. Those on the other side slip away forever. We were born on the inner slope. We belong to the basin. So the next time you look up at the night, remember this. You are staring into a continent of stars. Not a scattering, not a collection, not a postcard of pretty lights. A landmass of galaxies bound together by invisible forces older than life itself. We are tiny, fragile, temporary. And yet, we are citizens of something vast. We journey through the immeasurable heavens, carried by currents we cannot feel, drifting slowly home.